section 6.4 is about logarithmic functions. For all real numbers y and all positive numbers a, which we're going to talk about later in section 6.6, where x doesn't equal 1, y of log base a of x is equivalent to x equals a to the y. That means they're inverses, right? One undoes the others. The expression log base a of x actually represents the exponent to which the base a must be raised in order to obtain x. So, my favorite example, if I had 3 equals log base 2 of 8, that's the same as 2 cubed is 8. These are equivalent statements. So logarithms, like I said, are the inverse of exponents, and logarithms undo exponents. Even for negative exponents, right? If I have 5 to the negative 2 power, that's 1/25th, and log base 5 of 1/25th is negative 2. So let's practice going back and forth from not only solving these logarithms, but going back and forth from logarithms to exponents. So log base 2 of 8 is 3. That means 2 cubed is 8. Log base 3 of 27 is 3, because 3 cubed is 27. Log base 5 of 625 is 4, because 5 to the 4th is 625. Log base 2 of 64 is 6, because 2 to the 6th is 64. Log base 4 of 64 is 3, because 4 cubed is 64. And log base 8 of 64 is 2, because 8 squared is 64. It's close call there. Now I want us to write these exponents as logarithms. So if I have 3 to the negative 4, that means that log base 3 of 1/81st is negative 4. If I have 5 cubed equals x, that means log base 5 of x equals 3. You could even solve for x then, right? 5 cubed is 125. 5e to the x equals 7. That means that log base e of 7 equals x. Friendly note, log base e is the natural log, which I think I might have talked about in the last section. So I'd have natural log of 7 equals x. If I have 6x equals 136, that means log base 6 of 136 equals x. Well, here we know that x is negative 2. If I have x to the 4th equals 81, that means log base x of 81 equals 4. Well, I could solve for x here too. That means x is 3, because 3 to the 4th is 81. So log base 3 of 81 would be 4. I can also use rewriting equations as exponents to solve logarithmic equations. If I write this as 3 squared equals 4x minus 7, that means 9 equals 4x minus 7. I can add 7 to both sides. 16 equals 4x, divide both sides by 4. 4 equals x. Let's try this again with this next problem. If I have log base x of 42 equals 2, that gives me x squared equals 49, right? So I'm going to take the square root of both sides. X equals plus or minus 7. But as we'll talk about in chapter 6, I can only have positive bases, so my answer is only going to be x equals 7. So, like I said, logarithmic functions are the inverses of exponential functions. So if I have a logarithmic function with base a, its domain is going to go from 0 to infinity, and its range is going to go from negative infinity. But if I had f of x equals a to the x, its domain would be from negative infinity to positive infinity, and its range would be from 0 to infinity, right? Because they're inverses, their domains and their ranges are swapped. So let's take a look. Here's a visual. So if I have f of x equals 2x, f of x equals log base 2 of x is going to be its inverse. So for example, I know that if I have x is 2, y is 4, right? Because if I have f of 2 for my exponential function, that's going to give me 4. If I have for my logarithm, if I take f of 4, that's going to give me log base 2 of 4, which is 2. So I have the point when x is 4, y is 2. We know this is true. When I have inverses, my x and y values are switched. So some key characteristics of log base a of x. The points 1 over a and when x is 1 over a, y is -1 are always on the graph. The point when x is 1, y is 0 is on the graph, and the point when x is a, y is 1 is on the graph. Why is that? Well, let's take a look. If I have f of 1 over a, that's log base a of 1 over a, which is going to be -1, right? If I have f of 1, that's log base a of 1, which is always 0. And if I have f of a, that's log base a of a, which is 1, using our logarithm rules, right? As long as a is greater than 1, it's an increasing function. If a is a fraction, then it's a decreasing function. My y-axis is my horizontal asymptote. My domain is from 0 to infinity, and my range is from -infinity to +infinity. So why don't we go ahead and graph the following function. We're going to state its domain and range. So I have f of x equals log base 3 of x. So here I've got some x values and some y values. Now I told you on the previous slide some really good x values to use. So I'm going to use when x is 1/3. When x is 1/3, log base 3 of 1/3 is -1. When x is 1, log base 3 of 1 is 0, and when x is 3, log base 3 of 3 is 1. So I've got 3 points. So I have when x is 1/3, y is -1. When x is 1, y is 0, and when x is 3, y is 1. So here's my function. Perfect. Remembering that this x equals 0 is my asymptote. So let's graph the function log base 3 of x minus 2. What do we remember? What do we remember about when we're graphing functions? Well, if I've got a negative, if I've got something inside the parentheses, right, it's going to shift my graph either to the left or to the right. In this case, it's negative, so it's actually going to shift my graph to the right. So if I have x before, for my function f of x equals log base 3 of x, I had when x was 1/3, y was -1. When x was 1, y is 0. And when x is 3, y is 1. Now we're going to be shifting my graph to the right. So now I have when x is, let's do blue for our new function. I have when x is 3, log base 3 of 3 minus 2 is 1, which is 0, is log base 3 of 1, which is 0. When x is 5, I have log base 3 of 5 minus 2 is log base 3 of 3, which is 1. When x is 2 1/3, I have log base 3 of 2 1/3 minus 2, which is -1. Okay, so we always can use our graphing rules. It's important not to forget those. So now I have when x is 2 1/3, y is -1. When x is 3, y is 0. And when x is 5, y is 1. So my graph was shifted, and I've got a new asymptote. My new asymptote is when x equals 2. because it was shifted 2 to the right. Friendly reminder, e is an irrational number, right? It's found by taking 1 plus 1 over n to the n as n approaches infinity. It's a limit. So it's this irrational number. It's really useful. I can't 100% explain why, but it is. And for all positive numbers x, like I mentioned a little bit earlier, the natural log of x is log base e of x. This is the natural log. Even though e is an incredibly unnatural looking number, it is the natural log. We can also have log base 10. If you see a log by itself, it's not lonely. It's just kind of denoted log base 10. We do work at a base 10 number system, so keep that in mind. So how do I solve exponential equations? Well, I can use logarithms. So if I take the natural log of both sides, I can move this x to the front. So I have x natural log of e equals the natural log of 12. Well, the natural log of e is 1, so I get x equals the natural log of 12. Now, if you plug this into your calculator, you will get an irrational number, and that's okay. On an exam, I prefer if you leave them in natural log form. On the homework, it may ask you to give them an exact value. So let's solve these next two again using the natural log. I'm going to take the natural log of both sides. That gives me 2x minus 1. Natural log of e equals the natural log of 5. Natural log of e is 1. I can add 1 to both sides. So I have 2x equals the natural log of 5 plus 1. Divide both sides by 2. I get that x equals the natural log of 5 over 2 plus 1 half. Last but not least, if I have e to the x squared equals 200, and I take the natural log of both sides, that gives me x squared. Natural log of e cancels, equals the natural log of 200. I then want to go ahead and take the square root. So I have x equals the natural log of 200 as my answer. Note, I cannot go ahead and simplify this natural log of 200 because it's not the square root of 200, it's the square root of the natural log of 200.